SwayamPrabha. Digital India. Educated India.
What is the second parameter that we can obtain? The second parameter which we are going to get is what is called as a peak time, TP. Okay. So what is the peak time? The peak time is that instant of time at which the output reaches the first peak of its overshoot. Okay, this is TP. Okay. So the peak time of the underdamped second order system is the instant of time at which the output response reaches the first peak, okay, as far as overshoot is concerned. Okay. So obviously you see that the output value is the maximum for all time, right, at peak time, is it not? Because in the second peak you see that the output at the second peak is lower than the first peak, because you have a decaying exponential multiplying the cos and sine terms, right? So the output of the first peak is going to be the maximum value. Then how can I get peak time? Differentiate that expression equated to 0, then solve, then minimum means? Okay, any other step? Okay, what do? You get the second derivative and see it's negative, right, for maximum, right? We need to do those two steps. See here, why are those two steps important? Here you have a graphical interpretation. So what he says makes sense, right? See here I have drawn the graph. Suppose if I didn't draw the graph and I ask you to find the maxima, right? What will you do? You will differentiate it once, equate the first derivative to 0, solve, then you take the second derivative and substitute the roots for which the first derivative was 0 and find out whether the second derivative was negative or positive, right? If it's negative, it was a maxima, right? Positive means it's a minima, right? So please do that. Okay, so let's do this. So why don't you do dy dt equals 0? Okay, I have to keep track of this. I think it would have been better if I am seeing this. Okay, so I am going to write here. You please independently do it. I correct? Right? The cos omega d terms, dt terms cancel off each other, right? The plus and the minus. So I am only left with the sin omega dt term, and this once again like a times b times c equals 0, right? E power minus zeta omega t once again not 0 because peak time is finite, and the term within the square bracket is also not 0 because it's positive, right? So what can be 0? Sin omega d t is 0. So that means that the solution for this thing is n pi by dp, right? Obviously n equals 0 doesn't make sense, right? So we say n equals 1, 2, 3 and so on. Okay, so that's what we have. Oh sorry, n pi by omega d, right? Sorry, correct? Yeah. Now of course you need to calculate the second derivative. So d squared yt dt squared is going to be, let's put this constant term outside. Then what we are going to have is that we will first differentiate the exponential term, and then we differentiate the sine term. So what can you say about the second derivative at t equals n pi? At t equals n pi, the first term is gone, right? Second term will be some exponential which is going to be positive, right, times cos n pi. Okay, for what value of n will be cos pi will be negative? The first value is n equals 1, right? Cos pi is minus 1, right? Is it not? I hope it's clear what I am doing, right? I took the second derivative. This is a constant term, okay? Then I just differentiated. Why does the first term vanish? At t equals n pi by omega d, the second derivative just becomes omega d plus zeta squared omega n divided by square root of 1 minus zeta squared multiplied by, first term vanishes because it becomes sin pi, right? That's gone, that's 0. So we get e power minus zeta omega n n pi by omega d, okay? That's a finite number anyway, okay? Times omega d times cos n pi. Now we see that for n equals 1, the second derivative becomes negative. See, for n equals 0 or 2 or something like that, the second derivative is positive, right? So that indicates a local minimum, right? So for n equals 1, like the second derivative is negative. So that's a maxima, and from our argument we see that that's the global maxima for this particular function, right? So as a result, the peak time is going to be equal to pi by omega d. Okay, is it clear how we got pi by omega d as the peak time, right? Now the third parameter is what is called as maximum peak overshoot. Okay, what is this maximum peak overshoot? Okay, so immediately we see that this value is y at Tp, right? This 1 I can write as y at infinity, right? Because as t tends to infinity, what is the value of y, right? At steady state value. Now, what is the maximum peak overshoot? What do you mean by overshoot? Overshoot is the value beyond which the output, goes over the steady state value, right? This is an overshoot, right? Is it not? Now the question that we are asking ourselves is, by how much am I overshooting the final value to the maximum possible extent. So that means that I should first look at this number, right? What is y at Tp minus y at infinity, right? That is the maximum overshoot, right, that I am having. So this maximum peak overshoot MP is defined as y at Tp minus y at infinity, typically normalized by the final value and by and large indicated as a percentage measure. Okay, that's how it is given, right? So now what is y at Tp? You substitute Tp equals pi by omega d into this expression. What do you get? We get 1 minus e power minus zeta omega n pi by omega d cos pi, right? That is minus 1. Then this guy is 0. So immediately we see that y at Tp is going to be equal to 1 plus e power minus zeta omega n pi by omega d. Do you agree? How we got this? Let me repeat this once again. If you go to this expression and substitute t equals pi by omega d, the second term vanishes, right? Because you get sin pi. First term you get cos pi is minus 1, so minus and minus becomes plus. You get e power minus zeta omega n pi by omega d, right? So that's what we get here. And this I can rewrite it as 1 plus e power minus zeta pi divided by square root of 1 minus zeta square. Why? Because omega d is omega n times square root of 1 minus zeta square, right? I use the definition of the damped natural frequency. Okay. In this case, y at infinity is 1. So what will I have? I have the maximum peak overshoot to be equal to 1 plus e power minus pi zeta divided by square root of 1 minus zeta square, that's y at Tp, minus 1 divided by 1 multiplied by 100%. So maximum peak overshoot will be e power minus zeta pi divided by square root of 1 minus zeta square times 100%. Okay, so if someone says, damping ratio is 10%, that means that e power minus zeta pi by square root of 1 minus zeta squared is 0.1. Okay, that's how it should be interpreted. And immediately we can see that as zeta increases, MP decreases, right? So that's a counter, there's a trade-off that you have. See, we already saw that as zeta increases, the rise time increases, right? The system becomes slower, but the advantage is that the peak overshoot reduces. Why is that important? Because peak overshoot is indicative of by what magnitude does my output exceed the final value. See, just imagine this. Let's say if you open a door which is automatically closing, and then you pull it, enter, and then you leave it. You may see that it's oscillating. Ideally, do you want the oscillations to be very high or as small as possible? As small as possible, right? Because like we don't want to hit the next person, right? Then what will I do? I will essentially ensure that my damping is large. But if I make the damping large, you will observe that it takes longer for the door to close. That is indicative of rise time. So you would have observed that in many doors, like if you want fast closure, the oscillations will be larger, right? Because they will make the damping to be smaller, right? But then the price that we pay is that the oscillations are larger in magnitude. But if I do not want these oscillations, or I want the oscillations to be smaller, the price I need to pay is that I need to compromise on the rise time. Okay, so rise time and peak overshoot are two conflicting requirements, and considering these requirements, by and large, this is just a rule of thumb, by and large we design second order systems with damping ratios between 0.4 and 0.8. Okay, this is just once again a rule of thumb. Okay, common control design practice. Like by and large, we want to design underdamped second order systems that have damping ratios between 0.4 and 0.8. We do not want damping ratios lower than 0.4 because the overshoot will be very high. Okay, although the rise time will be very small. We do not want damping ratios beyond 0.8 because the system will be sluggish. The overshoot will be low, but then rise time will be high. Then the system's response takes a longer time. Okay, so that is the trade-off. Okay, between rise time and peak overshoot. Is it clear? Okay, so the last parameter which I am going to touch upon is settling time. This I am going to leave it to your homework. I am just going to give you the expressions. You figure out how we got them. Okay, the settling time once again is the time taken for the output to settle within a band, right? So if you take a plus or minus 2% band, the expression for settling time is 4 divided by zeta omega n. If you take a 5% band, the settling time is plus 3 by zeta omega n. Okay. By default in this course, if I say settling time, we are dealing with the 2% band. Okay. So in all problems that we are going to do in this particular course, if ever I talk about settling time, you must automatically consider 2% band. So that means that the settling time for a second order system, underdamped second order system will be 4 by zeta omega n. Settling time for a first order system will be 4 times time constant. Okay, that is the settling time we are going to use in this particular course. Is it clear? So how did we get this expression? I will leave it as homework. Okay, we derived for 3 expressions. That is what were peak time, rise time and peak overshoot. Settling time, you please do it. So once again, how do we visualize settling time? Let me go back to this graph. Let us say I take the 2% band. What happens is that I draw the upper band, upper limit and the lower limit. Okay, using this pink dotted line, and then you figure out what is the time after which the output settles to within this band, right? That's my settling time. Is it clear? I hope it's graphically also clear as to what we define by settling time, right? So these are the 4 parameters that we do. Okay, so these 4 parameters are based upon the transient response of underdamped, stable, second order, linear time invariant causal systems. Okay, so these are typical parameters that will be specified. Okay, like when we want to specify the responses. Is it clear? Yeah.
Settling time is the first peak after it's
Not first peak per se. Like what you can say is that it is the first instance after which the output settles within the band. See, for example, let's say the output settles here. Like just go one delta t ahead, and that's your settling time. Right?
So it's where the plus 2% intersects the.
Yeah. So see, the thing is, what is the first instant of time? Like after which what is it, no part of the output touches the band. Okay, that's how you do it. Okay. Yeah.
Characteristics are defined for only underdamped, or these are the same for underdamped, overdamped?
We are going to come there. Okay. So okay, his question was then. Yeah. 1 minute. Let me come one question at a time. His question was then, are these parameters common for even other types of systems? Okay. I'm going to answer that, okay, as we go along in the design process. Let me preemptively give you the reason. The reason why either time constant or these parameters are used is because, once again, the dominant dynamics that you typically find even in higher order systems either corresponds to a first order system or an underdamped second order system. What do I mean by that is that dominant poles will be either a pair of complex conjugate poles or a pole on the real axis, which corresponds to either a underdamped second order system or a first order system respectively. That's why we use this. Of course, it's an approximation, but it's an useful approximation nonetheless. Okay? Yes, please.
The above graph, the settling time, would it be right after the actual
Yeah, I just indicated qualitatively. Okay, if you want to zoom in and do this, you know, like see, this is the place where it comes out, right? I've just put it immediately afterwards. See, I don't know how to zoom in, right? Let's see whether it's see. Oops, I don't know what I did. Okay, but you get the picture, right? So see, this is where I just drew a freehand sketch, right? So, but you can see that this is the place where it last touches it, the pink line just to the right of it. Okay, that's settling time. Okay, yeah. The idea is that like after the settling time point, you know, the output should remain within the band. That's all. Okay, yeah. Fine. So now that we have looked at underdamped second order systems, let's qualitatively plot the step response of the three classes of systems, and then like I'm going to leave you with a homework problem. Okay, so let's do this. So if I plot y of t versus t, and we are looking at the unit step response of the three classes of systems, right? We are looking at the unit step response. Okay, of the three categories of systems. So if you have an underdamped second order system, what's going to happen is that the output is going to be something like this. Okay, oscillatory, and then it will settle down, right? So of course it won't exact, oops, I don't want to erase the entire thing, but you get the point, right? It will oscillate like this. If we had a critically damped, so this is an underdamped system. Okay, if we had a critically damped system, what's going to happen is that the output is going to start like this, and it's going to essentially never going to oscillate, okay, never going to cross 1, okay, but it will monotonically tend to the final value. So a critically damped system has no overshoot, but it is the fastest among second order systems without any overshoot. Okay. On the other hand, if you consider an overdamped system, an overdamped system will be extremely sluggish. Okay, so okay, not a great diagram. Okay, let me draw a nice smooth curve. Okay, it's going to be extremely sluggish. Okay, so we hardly design overdamped systems. Okay, so suppose if you do not want if you do not want oscillations. See, for example, you know, like to give an example, you know, like in an if you want to prevent collisions between vehicles, right? If you have two vehicles following each other, you don't want the vehicle spacing to oscillate like an underdamped system, right? Would you, right? See, you don't want to be in a vehicle which is traveling behind another vehicle and it coming and going forward and backwards suddenly, right? When it's stopping, you want a smooth, nice motion, right? So then, but then like you also would want the system to act as fast as possible. So you have two conflicting requirements. Then what you do is that you design as if it's a critically damped second order system. But of course, as I told you, critically damped second order system means zeta is exactly 1, and in real life it's very difficult to make it exactly equal to 1. Okay, we'll see when you design, right? But on the other hand, you know, like if you make zeta to be greater than 1, practically, you know, like it's going to be very sluggish. Okay, I'm sure you would have seen many of these automatic closing doors, right? You open it, it will close ever so slowly, right? That means that it's overdamped. Okay, it's very sluggish. Okay, the damping ratio is extremely high, because what is damping ratio? C divided by 2 square root of mk, right? For first 1 degree of freedom linear motion, right? So you see that if the damping ratio is very high, things will be very sluggish, right? So that's an overdamped system. Okay, so as I told you, by and large we are going to design as control designers, we would be by and large. Okay, once again there can always be exceptions. I told you one exception, right? By and large we design underdamped systems with damping ratios between 0.4 and 0.8. Okay, that's just a rule of thumb. Okay, there is no hard and fast rule that this is the only way to design control systems. No. Okay, yeah. So what I am going to leave you with are two homeworks. Okay, first find the unit step response of critically damped and over damped systems. Okay, second, find the unit impulse response of underdamped, critically damped and overdamped second order systems. Of course, it goes without saying that we are dealing with second order systems. Okay, so that's what I want you to do. Okay, so please do these two exercises. Okay, and so this essentially gives a broad overview of what we wanted to look at in the systems block, right? As I told you, right? So starting tomorrow, what I will do is that I will provide you with an overview of what options are available in the controller block before we go for further analysis. Okay, so that's what we are going to do tomorrow, right?